Hello, we will start by 3-5. Hello everyone, welcome to second week of the course Introduction to Semiconductor Devices, being taught by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25E92, and this is a live problem solving session by me, that is Mayank Goyal, and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Naresh Kumar Imani, who is an associate professor at in the Department of Electrical Engineering, IIT Hyderabad. So the modules for this week is carrier properties, intrinsic carrier density, Fermi level, donor and acceptor impurities, Fermi level in extrinsic semiconductors, temperature dependence of carrier density, generation and recombination of carriers. So this session is being held at every Sunday 6 p.m. to 8 p.m. But due to some work, it had to be shifted this week. But it will continue at the same time, Sunday 6 p.m. to 8 p.m. at this Google link. So first we will do a lecture recap of this course. So this 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 is material provided by the recap material provided by the professor. So the first topic is effective mass. So in an ideal band that is not interacting with any other material, so the band is considered to be flat, and the mass of electron is considered to be the effective mass of electron is considered to be the same as the rest mass of electron, that is m naught 9.1 into 10 to the minus 31 kg. But as soon as you bring two atoms or more atoms together, the bands start interacting and they form a parabolic shape, which we had in a lattice. The bands form a parabolic shape, which we had studied last week. So in a parabolic shape, when you calculate the mass of the electron by fitting in the equations, you will find that the mass of the electron has changed. So it is now not behaving as it is now behaving as it at a different mass. So that is called effective mass, and it is calculated by approximating the band edges of the by fitting a parabolic equation. So you use the parabolic equation, you put in the value for energy versus k, and you get this. So here you see that the mass is inversely proportional to the curvature of the band. So the more curved the band is, the higher will be the mass, or the lower will be the mass. And we can similarly the apply the same analogy to the holes, and we can calculate the effective mass for holes also from the curvature. Next up is carrier concentration. So in an ideal semiconductor, that is an intrinsic semiconductor, where the number of electrons and number of holes are equal. There at thermal equilibrium, the electron and hole concentration is given by this formula: n naught equals to nc experimental minus ec minus ef by kt, and p naught equals to nv experimental exponential minus ef minus ev by kt, where ec is the value of the conduction band, the minima of the conduction band. Ev is the value of the maximum of the valence band, and ef is called Fermi level. That is, at Fermi level is your energy below which above which there are no electrons at 0 Kelvin. That is, at absolute temperature, all the electrons below Fermi level, all the electron states below Fermi level are filled, and all the electron states above Fermi level are empty. So that is called a Fermi level. And then you can combine this to get this formula: ni square equals to nc nv exponential minus eg by kt, where ni is called your intrinsic carrier concentration, and it is given by n naught. Ni square is given as n naught into p naught, and if you solve this, you will find that your Fermi level is, for an intrinsic semiconductor, the Fermi level is closer to the band mid gap, which is mid gap is your basically halfway between your EC and EV, and you can calculate the Fermi level minus mid gap Fermi level with respect to mid gap by using the formula EFI. This is the intrinsic Fermi level. For if we dope the semiconductor, the Fermi level will change. That we will see in the next part. EFI minus E mid gap 3 kT by 4 ln MP star by Mn star, which is the effective mass of hole and effective mass of electron. Now we come to extrinsic semiconductor. So that is where the carrier concentrations of electrons and holes are not equal; they are different. So here the the carrier concentration are different. So now the formula is given as n naught equals to ni exponential ef minus EFI, which is EFI is your intrinsic Fermi level, by kT. And similarly for P naught, Ni exponential EFI minus EF by kT. So EF is a Fermi level for the doped semiconductor, and EFI is a Fermi level for the intrinsic semiconductor. You can also write it in terms of Nd and Na, which are your donor and acceptor concentrations. So how much doping you have done for the donor atoms and how much doping you have done for the acceptor atoms. That is given by Nd and Na. So you can write it as N naught equals to Nd minus Na by 2 plus square root of Nd minus Na by 2 plus Ni square. Similarly, for P naught, you instead of Nd minus Na, you write Na minus Nd. And this is called as mass action law. Ni square is equal to N naught P naught. For an intrinsic semiconductor, N naught and P naught are equal, so it will be N naught equals to P naught equals to Ni for an intrinsic semiconductor. But for an extrinsic semiconductor, the values of N naught and P naught are different. And the Fermi level position can be calculated as from if you rearrange this formulas, you can write it as EF minus EFI equals to KT ln N naught by Ni, or EFI minus EF equals to KT ln P naught by Ni. So the K here is the Boltzmann constant, KB. So generally all these formulas are written in terms of EV. So we write for T equals to 300 Kelvin, that is 27 degrees Celsius, which we consider to be room temperature, in our calculations. The KT is given as, if you calculate the KT for T equals to 300 Kelvin, the KT comes out to be around 25.9 milli electron volts. So you should remember that value, 25.9 milli electron volts, because that will help you solve a lot of numericals. Now we come to drift current density, and drift velocity, which which applies to the current flow in the semiconductor under an applied electric field. So your current density is given as E mu n n plus mu p applied electric field equals to sigma applied electric field. So your sigma is your conductivity. Your mu n and mu p are your electron and hole mobilities, and this epsilon is your electric field. N and p are your electron and hole concentrations. Similarly, you can calculate drift velocity as E tau epsilon by m star, where your E is the mass of is the charge on an electron, which is 1.9 × 10⁻19 coulombs. Tau is your mean time between collisions. So higher tau means higher drift velocity, and that will that would mean a higher mobility, higher current. So these were basic things that you need to remember. Now we come to the recap of the course. So this we learned last week, that electrons and holes in a semiconductor so there is two types of representation. One is physical space representation, where you show the physical positions of the electrons of the part of the lattice positions, and where the electrons and holes are. So we are studying physical space versus energy band representation. The physical space representation is, you show lattice positions and where the electrons and holes are situated based on the lattice positions, where energy band is in the momentum space, which is the reciprocal space of the physical space. So there we talk in terms of momentum k. and we talk in terms of energy band. So how the energy band changes versus momentum. So at zero momentum, which is called the central position, we see that in this case the valence band is, so we have, so when the in the lattice we have seen that there are generally two bands, valence band and conduction band. Valence band is where all your all your all your filled atoms are, and conduction band is where all your empty energy bands are, and the gap between the highest point of the valence band and the lowest point of the conduction band is given as your band gap. So if the both the maximum of valence band and the minimum of conduction band, they lie in the same momentum point, then they're called direct band gap materials. And if they lie at different momentum points, like in this figure, then they're called indirect band gap points. So some examples of direct band gap points are gallium arsenide and other 3,5 materials, whereas indirect band gap are silicon and germanium. And so when you provide energy to our, the electrons in the valence band can absorb energy, and they can rise to the conduction band, and they leave behind a space that is called as hole. So this process is called electron hole pair generation, which we have studied in the last class. Now we come to effective mass. So we know that, so when the when we in when the electrons are non-interacting, their energy bands are flat and their mass is equal to the rest mass of electron m naught. But when they are in a periodic lattice, then the energy band looks like a parabola. And if we solve the parabolic equation, we find that the mass of electrons is different than the regular mass m naught, and this new mass is called m star, or m effective mass. So we can solve this by applying the parabolic equation to this curve. So using the parabolic equation at any point on the curve, we can calculate the effective mass at that particular point. But generally the effective masses are calculated at the minima and the maxima points. And if we apply, we can then all the force equations that we use, we then use the effective mass to calculate the effective force on the electrons that they experience inside the semiconductor, which is two types of forces. One is the force from the applied electric field. If you apply an electric field, that will create a electric force. Other than that, it is also having electromagnetic interactions with the other electrons in the lattice and other atoms in the lattice, and the combination of that is your F total. So, but the internal forces from the lattice are very complex and cannot be calculated. So we only consider the external force, and the effect of the internal force is then accommodated in the m star. So then we can write F external equals to m star A. So this m star now has all the interactions between within the lattice structures, lattice atoms and electrons, that is encompassed in this m star, and it is calculated using the by applying parabolic equations. So you can see here, the more the curvature of the parabola is, the lesser will be the mass of the electron. So the highest mass of electron will be for a for a perfectly flat band, and that is given as m naught, or 9.1 into 10 to the minus 31 kg. And as it becomes more and more parabolic, more and more curvature, your effective mass reduces. So it can be point 9 m naught, point 1 m naught, 0.01 m naught, depending on the curvature of the bands. So it is given by the dispersion equals to h cross square k square by 2m. So your h cross square 2m is can be written as your curvature. So you get m star as m effective mass is h cross square by 2c, where c is your curvature of the band. And from this, then you can calculate other parameters. So typically in case of silicon, your m star is generally between zero point 0.3 to zero point 0.5 m naught. So this formula you can apply for both EC and EV. So for EC, it's applied when the band is facing up. For EV, it's applied when the band is facing down, because we consider holes to be opposite of electrons. Next is, so generally speaking, all the all the all the states in valence band are filled, and all the states in conduction band are happening, but at a finite temperature, you will have some electrons in the conduction band and effectively some holes in the valence band, and that is due to thermal generation of electron hole pairs. So for silicon, the at 300 Kelvin, your for intrinsic silicon at 300 Kelvin, you generally have around 1.5 into 10 to the power 10 per centimeter cube electron concentration at which is what your carrier density is. Since these electrons are movable, they can contribute to your current flow. And this plot gives you the carrier densities at different temperatures for different materials. So it's for gallium arsenide at 300 K, you will have 2 into 10 to the power 6 per centimeter cube. For germanium, 2.5 into 10 to the power 13 per centimeter cube. For silicon, 1.5 into 10 to the power 10 per centimeter cube. This is called your intrinsic carrier density, where your number of hole concentration, electron concentration is equal. So your N equals to P equals to Ni, and it is given as Ni equals to some constant exponential minus Eg by 2 kT. So that if you plot, you get this equation. So you take log, this log C, you can ignore in the equation. So if you take, if you are given this graph, you can calculate the slope of this, and from the slope you can calculate the Eg, because Eg is your log Ni minus log C into 2 kT. So Now we come to doping of semiconductors. So typically the silicon is purified up to N9 purity, that is 99.7 times 9. So you have 10 in total. There are 9 nines, 2 before decimal and 7 after decimal. So that is the impurity is less than 10 to the minus 7%. So now, so this is highly pure silicon, so the impurities are negligible. So we consider this to be intrinsic. So all the movement is from the pure silicon lattice. There are no impurities that contribute contribute extra electrons, or they take in electrons from silicon. So your hole and electron concentration are equal. So there are two types of dopants. One is donors, which give electron to the silicon lattice, and one is acceptors, which take electron from the silicon lattice and leave behind a hole in the lattice. So your group 5 elements, phosphorus, arsenic, antimony, they are they are considered donor dopants, and generally we use phosphorus and arsenic for doping. We don't use antimony. Similarly, group 3 elements are called acceptors: boron, gallium, indium, aluminium, and we use boron as your boron as our doping dopant, because all the rest of them are metals. So if we dope with metals, that cause some additional issues. So we prefer boron here, and phosphorus and arsenic for donor doping. So when you dope it with phosphorus, what happens is the phosphorus replaces a silicon. So four of the atoms of the so phosphorus has 5 valence electrons. So four of those bond with the four neighboring silicon atoms, but the fifth electron is extra, which remains unbonded, and that increases your electron concentration in the lattice. Similarly, for boron, what happens is it only has three so it only has three valence electrons. So it makes 3 bonds, and one of the bonds remains empty, which it then fulfills by taking in extra electrons from neighboring atoms. So that creates a that that creates a vacancy of electrons in the lattice, and that vacancy of electron is called a hole. So it increases hole concentration at equilibrium. So when there's an excess of electrons, it is called an n-type material. When there's an excess of holes, it is called a p-type material. So these donor or acceptor atoms, they don't they don't contribute to your current conduction, as they're fixed in the lattice, but the only the electrons and holes can contribute to the current flow. Now, how the doping changes your energy bands. So what happens is that it creates an energy level near when there you have donor atoms. It creates an excess of electrons, so it creates a donor energy level that is close to conduction band. And when the conduction band requires electrons, it takes in from this donor level instead of going all the way to the valence band. So it has it has to take effectively less amount of energy is required to increase the electron concentration in the valence band. sorry, in the conduction band, the number of electron concentration becomes higher due to less number of energy required. So at thermal equilibrium, there are number of more number of electrons than number of holes. So that is why in an n-type semiconductor, there is higher electron concentration than there is hole concentration at a particular temperature. Similarly, when you have an acceptor dopants, what happens is it creates an acceptor energy level near the valence band, and at room temperature it requires very less amount of energy for electrons to go from valence band to this acceptor energy level. So at room temperature, it all the acceptor energy levels the acceptor energy level gets filled with electrons from the valence band, leaving behind a large concentration of holes in the valence band. So in the p-type materials where you have been doped by acceptor atoms, you have a higher number of hole concentration than the higher number of electron concentration. And then this is your electron concentration versus temperature. So in the moderate temperature regime, and for an this is for an extrinsic semiconductor. So in the moderate temperature regime, that is like 200 to 400 Kelvin, something like that. Your carrier concentration remains constant and is equal. It's almost equal to your donor energy or acceptor energy concentration. Whereas in whereas for very low temperatures, you have something called freeze out, where the electrons stop electrons are not going to the energy states in the acceptor or donor energy bands. They are not getting filled or emptied properly, so there is less number of electron or hole concentration in conduction and valence band respectively. So your concentration reduces drastically as you go lower temperature, whereas as you go very high temperature, the thermal energy overpowers other your band gap, and then thermal energy overpowers your all the band gap energy, and then you have something called as impact ionization, which results in a large number of electron hole pair generation, and this generation is independent. This generation is independent of your dopant and or acceptor concentration, because it is going from directly from valence band to conduction band, and your hence at very high temperatures you have higher number of carriers, and that number is equal to your intrinsic carrier concentration at that temperature. So your Fermi function is given as 1 upon 1 plus exponential E minus EF by kT. So this gives the probability of having an electron in a particular energy level at a particular temperature. So so below Fermi level, your probability is almost 1, and above Fermi level, the probability goes very soon to 0. And that gives your Fermi level in your semiconductor, so which lies near the for intrinsic semiconductor, the Fermi level lies near the band gap. We have already seen that in the initial slides. And for extrinsic semiconductor, the Fermi level lies closer to the valence band or conduction band depending on the concentration of electrons and holes. So that we will see here again. The Fermi function, it gives the probability of finding electron at an energy level, a particular energy level E, and their EF is called Fermi energy or Fermi level. So at 0 Kelvin, all the energy states below Fermi level are completely filled, and all the energy states above Fermi level are completely empty. For some finite temperature like 300 Kelvin, 400 Kelvin, it there's a probability associated with it, but very near the near the Fermi level, there's a probability associated with it, but far away with the Fermi level, it's still 1 and 0. So you can solve this, you will get all these four equations. So now if we calculate using, if we use this formula on our semiconductor, that is f of EC equals to 1 plus 1 upon 1 plus exponential EC minus EF by KT. That is probability of finding an electron at this level, EC, and the probability of finding a hole at the EV level is given as f of EV 1 plus 1 upon 1 plus exponential EV minus EF by KT. And so that is the probability of finding an electron at this EV level, but the finding an hole will be opposite of finding an electron. So the probability of finding a hole is given as 1 minus f of EV. So for intrinsic semiconductor, N and P are equal. So f of EC equals to 1 minus f of EV, which is which if you solve, you will get E of Fi equals to EC plus EV by 2, which is the mid gap position. So E of Fi equals to E of I, which is middle of the band gap. So you so NC or NV are very important terms when we are doing carrier concentration. We are calculating carrier concentration. Generally, these values are given to you for any question. So these values come from 2 into 2 pi mn star kt by h square 3 by 2, and for NV it's instead of mn star it's mp star. So these values have been calculated. For silicon, NC is 2.8 to 10 to the 19 per centimeter cube, and NV is 1.04 into 10 to the 19 per centimeter cube. So these values are generally not asked. You are not generally asked to calculate these values. These values are generally given to you because these depend on your effective mass values, and effective mass values can vary heavily depending on your structure of the band. So if there's so band structure calculation is a very big research field, but it's not very accurate. So we generally consider mn star and mp star to some reference values, but they are not always accurate. Hence, you won't be asked to calculate NC and LV values generally. Now, using NC and NV, you can calculate the electron concentration and hole concentration as N naught equals to NC exponential EC minus EC minus EF by KT, and for hole P naught equals to NV exponential minus EF minus EV by KT. So you calculate this for So for intrinsic, it comes out N naught and P naught are equal to Ni. So your Ni square is then N naught P naught, and that is you multiply both of these, so you get Ni equals to under root Nc Nv exponential minus Eg by 2 kt, and then your and so we had already seen it's Ni is equal to C exponential minus Eg by 2 kt. So your C is then under root of Nc Nv, and then you can then put these back into values N naught and P naught. So you get N naught equals to Ni exponential Ef minus Ei by kt, and P naught equals to Ni exponential Ei minus Ef by kt. From there you can calculate the Fermi level for extrinsic semiconductors. So your, let's say your dopant concentration is 10 to the power 3 per centimeter cube. So N naught is then given as Nd plus Ni, which is all. So Ni is generally 10 to the power 10. So this is 10 to the power 3 plus 10 to the power 10 approximately equals to 10 to the power 10, which is Ni. And if it's given as 10 to, Nd is given as 10 to the power 15, then your N would be Nd plus Ni approximately equals to Nd. So Ni will be cancelled out. So as you increase Nd, the Fermi level moves closer to Ei, closer to Ec from Ei, and as you increase Na, that is make the material more and more p-type, the Fermi level becomes closer to Ef. So for higher Nd, the Fermi level becomes closer to Nc. For a higher Na, the Fermi level becomes closer to Nv. So this is the formula for, this is a example where you have an n-type semiconductor. So the with where you have given Nd equals to 10 to the power 15 per centimeter cube. So that will be your N equals to Nd, and Ni is given as 10 to the power 10 per centimeter cube. From there you can so from by rearranging the previous equation, you can calculate the Fermi level as Ef minus Ei equals to kT ln Nd by Ni. So for 300 Kelvin, I told you the kT is taken as 25.9 milli electron volts, or also known as 26 milli electron volts, and then ln you can convert to log, that is 2.303 log 10 to the 15 by 10 to the 10, that is log 5, that is 5, that is 5. So you multiply it, you get around 0.3 ev. So which means Ef has changed by a value of 0.3 ev from mid gap, and the total mid gap value is 0.56 ev. So you have a gap of 0.26 ev. For it, Ef is closer to Ec at 0.26 ev. And you can also calculate the hole concentration by the formula Np equals to Ni square. So taking Ni is 10 to the power 10 or 10, 1.5 into 10 to the power 10 depends on what we have been given in the question. It comes out to be 10 to the 5 per centimeter cube. Similarly, if you are given a p-type semiconductor, you will be given the value of acceptor concentration instead of hole concentration. Then instead of all the calculations remain the same, but instead of going above, the Fermi level comes below to towards the valence band. And then a p hole concentration is 15, and then electron concentration is 10 to the 5. And these are called your majority and minority carriers. So if your electron is there are more electrons than holes, then your electron is majority carriers and holes are minority carriers. If in a p-type material the holes are more, so the holes are majority carriers and electrons are minority carriers. So as you dope more and more n type, that is, you put more and more donor atoms, you will see the Fermi level goes more and more towards the EC, and it is possible that it can touch EC. Similarly, for P type, as you add more and more receptor, the Fermi level goes more and more towards EV, and it can effectively touch EV. And so there is a limit we have set, which is called 3 kT limit. So EC minus EF is greater than 3 kT, or EF minus EV is greater than 3 kT. That is approximately 75 milli electron volts. So if there's a gap of 75 milli electron volts here, or a gap of 75 milli electrons volt here, minimum gap, that is, then only we consider the equations that we have used previously valid. Otherwise we, and that is called non-degenerate doping. So if your EF becomes much more closer than EC, then we consider it to be degenerately doped, and then all the equations that we have just learned become invalid. Then we have to use different equations to solve our problems. So this is the summary we have just learned. Now we learn about impact of doping. So this we have learned that group 5 elements act as donors, group 3 elements act as acceptors, and for n type the Fermi level moves closer to EC as you increase your donor level, and in this case, P type case, it moves closer to EV as you as you as you keep increasing acceptor level. So as you with temperature for the Fermi level for an extrinsic materials changes with the formula EF minus EI equals to KT ln ND by NI, and here your Ni itself is dependent on temperature. So what effectively happens is your both of these for moderate temperatures, both of these temperature dependence cancel out each other, and what happens is that your Fermi level and and your your whole electron concentration remains constant for moderate temperatures, but for low temperatures you have freeze out, where the number of there is not enough energy for complete ionization of your acceptor and donor energy levels. So the concentration is lesser than the available electrons, whereas for very high temperatures you have enough energy to have band to band electron hole pair generation, so which overpowers your your donor and acceptor level concentrations. So your material becomes starts behaving like an intrinsic material again, and your concentration then increases as a function of intrinsic error concentration, which is dependent on temperature. So this is how it has been calculated for different at different n values and different temperatures, how your EF minus EI changes. And you can see that they are more or less they don't change a lot of a huge they have a they don't change a lot for moderate temperatures. Then this is we come to charge neutrality relationship, which is your electron and hole concentration is the number of electron and hole concentration available for current flow compensate for the your impurity generated by your donor and acceptor levels, the charge impurity generated. So you have your nd minus n naught minus nm nd plus minus n naught minus na plus p naught equals to 0. So this is, as we here this equation assumes that your nd is greater than na. If na is greater than nd, then you will have na minus p naught minus nd plus n naught equals to 0. Does not really matter. Since it's equals to 0, the sign does not matter much. So it basically means your number of total number of charge positive charges will equal the total number of negative charges. So you put, instead of p naught, you can put ni square by n naught. So you will get this nd minus na n naught minus n naught square minus ni square. You rearrange it, you will get n naught equals to nd minus na plus under root of nd minus na square plus 4 ni square whole divided by 2, or you can write it as nd minus na by 2 plus nd minus na by 2 square plus na square ka whole square root. And this is if nd is greater than na. If na is greater than nd, then you can calculate p naught with using the formula na minus nd by 2 plus square root of na minus nd by 2 square plus na square. So these formulas are only valid for the majority carriers, because your nd minus na or na minus nd, it should be greater than nd should be greater than na here, na should be greater than nd here. So this is one example problem. So at 300 Kelvin, you are given nd equals to 10 to the power 16 and na is given as 0. So you have only done donor doping, not acceptor doping. So first we use this, so na is 0, so we just have to do nd. So and na is taken as 1.7 10 to the power 10 per centimeter cube. So we put this formula here, we calculate, then you can calculate this by putting na equals to 0, nd equals to 10 to the power 16 and ni equals to 1.7 10 to the power 10. If you solve this, so you will get that na is approximately equal to nd and p naught, then you can, so na is equals to here 10 to the power 16, then and then p naught you can calculate by just doing ni square by n naught. So that gives you electron and hole concentration. So now when na and nd are very similar, so nd is 500 10 to the power 15, na is 2 into 10 to the power 15. So nd minus na is 3 into 10 to the power 15. So here it again ni will cancel out because it's much less than 10 to the power 15. So here you will get n naught, your n naught equals to 3 into 10 to the power 15, and then p naught can be calculated as ni square by 3 into 10 to the power 15. Now we come to current flow, carrier drift. So when there is no electric field, the electrons and holes move in random directions. So due to this random motion, the net movement is 0. So hence net current flow is zero. But when there's an applied electric field, then the electrons will move in the direction of the electric field, and the holes will move in the opposite direction of the electric field, and then their the flow of electrons and holes can be calculated in terms of drift current. So this is drift current density, which is given as rho Vd or NeVd, where N is your number of electrons, electron density, E is your charge of electron, and Vd is your drift velocity. And instead of this, you can also write it as Ne mu epsilon, where epsilon is your electric field, mu is your mobility. So this is the value for electron conduction. So for whole conduction, instead of N, you will write P. The mu here, the mu is the electron mobility. There, the mu will be hole mobility, and from there you can get Vd equals to mu epsilon, where mu is your mobility, and the total will be the sum of both electron and hole conductions. So drift current density will be E n mu n plus P mu P into epsilon, where mu is given as E tau by m star. So for silicon, the values for mobilities are 1350 for whole electron mobility and 480 for hole mobility. So since holes are closer to the lattice than electrons, because holes are basically the electron vacancies on the atoms, so they're closer to the lattice and they feel higher lattice forces, which reduces their which reduces their drift collision time. So they're they're colliding more often, so hence their collision time reduces, and hence their mobility is also less. So we can calculate the conductivity using this formula, J equals to sigma E. So conductivity is then E n mu n plus P mu P, and for intrinsic silicon it's around 100 kilo ohm centimeters. And here you can see how the doping changes the value of the resistivity. So does not matter if you are doping it p type or n type, in both cases the value of resistivity decreases. So this is how they behave in an electric field. So they acquire kinetic energy from the field, and hence they move electrons in the direction of the field, holes in the opposite direction of the field. This is how it is. So this was the recap of the course. And now we'll go back to our PPT and we will do some practice questions. So these are questions that are similar to your assignments and your exams. So the first question is, choose a correct statement out of these two. So the first statement is, in a doped semiconductor, the ionized dopants, that is donors or actors, can freely move in the lattice. Second, in a doped semiconductor, the ionized dopants do not directly contribute to the current flow. So first option is correct. First statement is correct. Second statement correct. Both are correct, or neither of them are correct. So you can say your answer or write it in the chat. That is right. The answer would be two. That so the ionized dopants are fixed in the lattice, and hence they cannot contribute to the current flow. So option one is incorrect and option two is correct. The electron concentration in a piece of silicon maintained at 300 Kelvin under equilibrium condition is 10 is to the 5 per centimeter cube. The whole concentration is 10 is to the 15 per centimeter cube, 10 is to the 5 per centimeter cube, 10 is to the 10 per centimeter cube, or this is not sufficient information. Take Ni equals to 10 is per 10 per centimeter cube. So the answer to this is 10 is by 15 per centimeter cube. So use the mass action law, that is Np equals to Ni square. So N you have given as 10 is by 5, Ni you have given as 10 is by 10. So P you can calculate as Ni square by N, that is 10 is by 20 by 10 is by 5, that is 10 is by 15 per centimeter cube. Next question. A particular intrinsic semiconductor has a resistivity of 1000 ohm centimeter at T equals to 300 Kelvin and 10 ohm centimeter at T equals to 330 Kelvin. If the mobility of the carriers and energy band gap remains unchanged with temperature, the band gap of the semiconductor is dash. So 1.13 eV, 1.23 eV, 1.33 eV, 1.43 eV. So you have to use the formula Ni is proportional to T power 3 by 2 exponential minus Eg by 2 kT. So the answer to this question is, hello? So the answer to this question is 1.23 eV. So you know the conductivity is proportional to your carrier concentration, that is inversely proportional to your resistivity. So instead of Ni you can write 1 by resistivity. So and then you can, so this value is your constant, only your temperature is changing. So that then you can solve this here, and you will get, if you solve this, so by putting rho 1 by rho 2, that is 100 by 10, and temperature 10 by 100, temperature would be then T2 by T1, which is 330 by 300, and your band gap is also then Eg2 by Eg1, Eg2 minus Eg1. And if you solve for this, you will get the change in band gap to be 1.23 eV. Consider silicon doped with boron to concentration of 4 into 10 to the 15 atoms per centimeter cube. If Ni is your 1.5 into 10 to the 10 per centimeter cube and Vt is 26 millielectron volts at T equals to 300 K, compared to undoped silicon, the Fermi level of doped silicon shifts by 0.15 eV towards EV, shifts by 0.325 eV towards EC, shifts by 0.325 eV towards EV, shifts by 0.25 eV towards EC. So the answer to this would be it shifts by 0.325 eV towards valence band. So you use the formula EI minus EF equals to KT ln Na by Ni. So you are given the value of Na. So boron is your acceptor level. So you use boron is an acceptor atom. So use Na and not Nd. So it becomes p type. Hence the movement is towards valence band. So use the formula Na equals to 4 into 10 to the power 15. Ni is 1.2 10 to the power 10. And KT is given as your KT is then your VT 26 milli electron volt. If you solve it, you get 0.325 eV, and since it's p-type, it goes towards valence band. Find the correct plot that depicts the position of the Fermi level corresponding to non-degenerate doping for an n-type and p-type material. So here the red curve is for n-type material, the green curve is for p-type material. So your y-axis is your energy level and x-axis is your doping level. So how the Fermi level is changing as the doping increases. So this one, this one, this one, or this one. So the answer to this is A. So as you increase the doping, your Fermi level goes closer to your conduction band or valence band. For N type, it goes closer to conduction band. For P type, it goes closer to valence band. Hence, this is the correct plot. Choose the incorrect statement regarding the mobility of carriers in a semiconductor material. The unit of mobility is centimeter square per volt second. Due to higher lattice forces experienced by holes, hole mobility is greater than electron mobility. For a semiconductor material, surface mobility is smaller than in the bulk. Mobility depends on temperature. Which of these four is the incorrect statement? So the correct or the incorrect statement here is due to higher lattice force experienced by holes, hole mobility is greater than electron mobility, which is the incorrect line. So due to higher lattice forces, the hole hole has a higher, so holes have a lower collision time as well as higher hole effective mass, and both of these contribute to lower mobility. So hole mobility is much lower than electron mobility. For an intrinsic semiconductor, M effective electron mass and effective hole mass are Me star and Mh star are effective masses of electrons and holes near the corresponding band edges respectively. At finite temperature, the position of Fermi level depends on Me star, not on Mh star, Mh star, not on Me star, both Me star and Mh star, neither Me star nor Mh star. So the correct answer here is both Me star and Mh star. So which is the formula that we have seen in the starting of the lecture. A piece of silicon is doped uniformly with phosphorus with a doping concentration of 10 to the power 16 centimeter cube per centimeter cube. The expected value of mobility versus doping concentration for silicon, assuming full dopant ionization, is shown below. The charge of an electron is 1.7 to the power minus 19 per coulomb. Coulomb. The conductivity in Siemens per centimeter of the silicon sample at 300 K is which formula? So the correct answer to this is 1.9 point Siemens per centimeter. So your conductivity is given as n nq nq mu n plus pq mu p. So you can ignore, since p is much less than n, you can ignore that term. So it becomes nq mu n, and all three values are given the question. 10 to the power 16, q is 1.7 10 to the power minus 19, and mobility you can calculate from the graph as 1200. So you multiply all that, you will get 1.92 into 1.92 Siemens per centimeter. So next question. The donor concentration in a sample of N-type silicon is increased by a factor of 100. Assuming the sample to be non-degenerate, the shift in the Fermi level in milli electron volts at 300 Kelvin is given that kT equals to 25 milli electron volts at 300 Kelvin, 165.5, 218.2, 115.5, 82.75. The correct answer to this would be 115.5. So we know EF minus EI is equals to KT ln ND by NI, and so the another, so since donor increased by 100 times, so now it will be 100 ND. So you subtract that, you get EF2 minus EF1 equals to KT ln 100, which when you solve you get 115.5 milli electron volts. Next question. For a non-degenerately doped N-type silicon, which one of the following plots represents the temperature dependence of free electron concentration? So the graphs is between log n and 1 by t. So which one of the four graphs is the correct one? So the answer to this is the plot A, where you have at low at moderate temperature you have a flat line, but at very low and very high temperatures you have a increasing trend where the mobility the concentration is increasing with temperature. So that is all the questions I had for today. Thank you for your attention.